Okay. Good morning, everyone. Welcome back. Today we'll do image refinement in 2D and 3D. Everyone has his favorite part of the whole process, and this is definitely mine. Because after doing all the hard work of the work at the microscope, like Laurie and Chris spoke about sample preparation, and the initial image processing that Paula spoke about on Friday, we now go into a process where we take these noisy images, which look rather ugly, and start calculating much cleaner two-dimensional class averages or even three-dimensional maps. So suddenly we can start learning all things about biology. So after what I will be discussing about, there will be another lecture about how you do some post-processing on your refined maps. And then after that, there will be interpretation as well by Leifu and by Leifu and Alan, sorry. But then, so today we'll do two-dimensional and three-dimensional image refinement, which could be alignment and classification both at the same time. So convention in the field, a whole toolbox of different programs have been used in different types of algorithms. So many of them I will not speak about. I will not speak about anything about multivariate statistical analysis, which have been very popular, no neural networks, anything like that. I will focus on multi-reference or single reference refinement of images, and I'll tell you what that means. And the reason why I do that is that most likely that's what you're going to use. Okay. The whole goal of doing image refinement would be to take these very noisy images and take an underlying signal, align it so that things that should be similar are on top of each other, and then sum them together so that by averaging over many noisy instances, we can actually increase the signal-to-noise ratio and get some useful information out of this. Okay, so I thought I'd first describe a bit from a different point of view, from mathematical one, the type of problem that we have, and then discuss with you 2D alignment and classification, then go into 3D and look into the Fourier domain as well. Okay, so as should have become clear by now, there are some inconveniences in cryo-EM images, cryo-EM imaging, and the most important one is that we have this damage from the electrons, so we can only image with very few electrons so that we have very large amounts of noise, okay? Now, then, as has been explained before, we need to defocus to get contrast, and this gives very strong artifacts. Remember the sinusoidal-like waves in the Fourier domain. So we have to correct for that. And then, because we have our particles, we have them in solution, we apply this to in a thin layer of vitreous ice in the grid, we actually can't experimentally control how these particles orient on the grids. So we also don't know which orientation each particle is. Is it a top view, is it a side view, etc. And then if this is a molecular machine which uses different conformations for its function, and that very likely might happen on your grid as well. If it's a complex, it might fall apart, it may be partial formation of your complex, etc. So then you would also have to define distinct classes which are all structurally similar in order to do averaging. Okay? Now, from a mathematical point of view, this boils down to an incomplete ill-posed and an inverse problem. So those are a few new terms which I would like to go through with you. Okay? So inverse problems are problems where one way of the problem is relatively easy. Okay? And in this case, if we would know the three-dimensional map of our structure, then simulating an electron microscopy image wouldn't be too hard. Okay? We would apply some projection operator. You can do this in real space as these line integrals that we discussed in lecture 2, or as taking a slice out of the 3D transform as we've seen before in a certain direction, which I will call phi. And then we have these artifacts of the CTF, this modulating function, which is the Fourier transform of the point spread function of the whole system, as we discussed also in lecture 2, and that we can just mathematically do either by a convolution in real space, or as we saw in lecture 2 more efficiently by multiplications in Fourier space, okay? And then our experimental images are very noisy, so we'd have to put some type of noise on top of that. That's actually not that easy to to simulate noise, but you could come up with something which resembles cryo-EM images quite well. Okay. Now that's what we call the forward model. Okay. Now the other way around is not so easy. Okay. So if you have a number of two-dimensional images which have a lot of noise, then to go back to knowing what the three-dimensional map was that underlied this structure is not that easy, okay? Because, well, we have this CTF, where some parts of some frequencies were actually 0. We don't know which orientation each of these particles is. And then even if we do, then we have all these two-dimensional particles, we would have to do some kind of a 3D reconstruction, okay? So that's then the inverse nature of the problem, that forward easy and backward isn't at all, okay? Now, I thought just for illustration purposes to do a bit of a simpler problem first. So we don't have a three-dimensional model where we have a projection in a given direction and CTF artifacts. Let's start with a two-dimensional image, okay? So just think of, perhaps you want to think of this as your protein adopting some preferred orientation, so you put it on the grid and you always see a top view, okay? So this is a noiseless top view, and because it's a two-dimensional image. Now, they're no longer projection operators, but they're just how is your particle rotated and perhaps translated if you didn't pick it in the center, okay? And phi then describes the rotation and the translation. And I'm going to ignore CTF effects to start with, okay? So that my experimental image can be described as a rotated and perhaps translated version of a given signal image plus some noise on top, okay? Okay, now then the incompleteness of the problem, what does that mean? Okay, incomplete data problems are very, very common in biology, and not only in biology, in many sciences. You can think of these problems as problems where part of the data could not be observed experimentally. Okay, and in our case, the incomplete nature of the data lies in this missing information that we just can't control experimentally, and unfortunately, there's not a label on our micrograph where every particle says this is class number 1 and it's in this orientation. Okay, that's unfortunate. The missing data is the orientations and the class assignments. Okay, now that becomes then rather difficult to solve, and typically one needs iterative methods, as we will see. And if it were to be complete, if there were these little labels on every particle, that would really make our life so much easier. Okay, so complete data problems would be very easy to solve. Okay, now of course for those of you who do X-ray crystallography, you also have a very famous incomplete data problem, which is the phase problem. Okay, so you happen to observe the intensities of your diffraction spots, but somehow the phases are lost in the experiment. It would be so much easier to do X-ray crystallography if every spot came with a little label with its what its phase was. Okay, so let's have a look. This is perhaps you can see what is the underlying signal image here. This is an incomplete data problem because they're all in different orientations and I haven't observed those. Okay, so the observed data are the actual images, the two-dimensional arrays of numbers there. Now, the missing data, I'll call those Y, are the orientations. Okay, now it's not necessarily that easy to find the true underlying signal in these images for this incomplete data problem. If it were to be complete, then that would be much easier because, we'll do this in a minute, if you have some description of the noise in it, then you could just say, oh, I can calculate an estimate for the underlying signal just by averaging over all these images. And I have enough noisy images of these, then I can average and retrieve the true signal image that underlies these noisy data. Okay? So that's easy. So then what do you do if you have an incomplete data problem, which is our case? Okay? Now that brings me then to two-dimensional alignment. Okay? Intuitively, it's easy. The problem is easy to understand. We just need to rotate all those penguins until they're all upside up. That's what we need to do. Okay? For our human brain, that's very easy. We've evolved a pattern recognition machine in our brain that's marvelous at recognizing murderous penguins running towards us and it's very easy for us to see that one is upside up or upside down, okay? Now, how do we tell a computer who can only do additions and subtractions to actually recognize that as well, okay? So the first option, and this is the one that has been used conventionally in the field, we have our model. Think of our model, the estimate of the underlying true penguin image, okay? We just expand that model with a whole set of new parameters, and those are y, so all the orientations of the parameters. So every image will get a rotation. This one is plus 45, this is plus 90, etc. Okay? So, and then we just have a much larger model to refine. Not only do we have to find what the underlying penguin image is, we also need to find all these orientations. That's option one. Option two is a more statistical one, and we're going to calculate the probability of observing the entire data set regardless of whatever orientation of image was observed in, and we'll go into a bit more detail later. But it involves an integration over all the orientations, so we're going to calculate the probability and do probability weighted averages, as we'll see in a moment. Okay? Now, option one in cryo-EM has always been called maximum cross-correlation, and we'll see in a minute why. For those of you who do X-ray crystallography, you've called these things least squares optimizations, okay? Now, the second one in both fields have been called maximum likelihood optimizations, okay? Now, let's have a look at the maximum cross-correlation approach first, okay? So, we have some initial guess about our penguin, okay? And we'll come back later about what that is. And now, what we need to do is rotate this image with respect to that one until it fits best. As said, your human brain, for your human brain, this is a very silly exercise and it's completely obvious. But for a computer, it isn't that easy, okay? So for a computer, the first image A, which could be our reference image, is just a two-dimensional array of pixel values, and the whiter it is, the larger the value, for example, and the blacker the smaller. And we have image X there as well, which is a similar array of pixels, and the values in that image is just different, okay? Now, what we need to do, we need to rotate, and rotation will involve some interpolations, etc., which I will not go into detail again, okay? But we have our little penguin there, and we have another one there, okay? Now, what we need to do is define some number, because that's what computers are good at, to describe how well does this picture fits with this one, okay? And already in lecture 2, I think we saw that perhaps it would be a good idea if every pixel here has a subscript j, okay? And then so aj will be the value of pixel aj. Then it could be good to minimize the square difference between the two images. If two images are the same and they're aligned, then their square difference will be 0. If one image is noisy, one image isn't, they will be aligned, their square difference will be some minimum, will be lower than square differences when the images are not aligned, okay? So this could be a good description of how well are my two images aligned, okay? As we already saw in lecture 2, you can change this notation to something like this. Okay? Now, this is the sum of the values of the image in A squared. Okay? That doesn't matter. It's invariant to what orientation X has with respect to A. And so is this one. So these two are like constants. And here we go back again to the similarity between cross-correlation or signal product and square difference, okay? So what we're gonna do, we're just gonna calculate this for this orientation, rotate the image, calculate again the value, and then in the computer we can just take a table where this is the rotation and this is the value of, that was an A, of that one, and we're gonna pick the minimum, okay? So let's have a look. We're going to rotate the image all the way around and store this value. Then we could make a little plot and just say, oh, this is where the cross-correlation was maximum, that was the square difference was minimum. So that's now the best rotation that this image is in with respect to this initial reference, okay? Now, that we can do for all the noisy images, and then we get some alignment Now it's not perfect yet, because the initial model that we had for our penguin wasn't perfect. Okay, it was some kind of a fuzzy picture of our penguin. So now all my penguins are more or less aligned, but what you can now do is take the average of them, and that will give a penguin image which is better than the original one, okay, but it's not yet perfect. So now thereby then becomes clear why these methods for solving these incomplete problems need to be iterative, because this one is better than that one. I can now feed this one back into the same process and iterate. Now, because this one is better, the angles that I get will be closer to the truth, and if I iterate this enough, I will finally get to the, hopefully to the correct estimate of my underlying signal, okay, if I have enough of these. Okay, good. Now, the maximum likelihood approach, and the first paper on this was done by Fred Sickworth in 1998 for just this problem, okay? Single reference alignment of two-dimensional images in real space, okay? What we have for maximum likelihoods, we do something very similar. We calculate some figure of merit, some measure where we compare how well does this image explain that one, or does it agree with that one, okay? It does so in a bit more statistical manner. It calculates a probability of observing the image given that that reference image in a given in any orientation, okay? Now, if this value, if I plot the value of this pixel here on an x-axis, okay, this is pixel value. And this now happens to be for pixel j, value aj, okay? Now, if I assume that there is Gaussian noise on top of this image, okay? And if I assume this is the correct underlying signal for this image, which it isn't as you can see, okay? But let's just assume for now this is the correct image. Then the most likely pixel value for pixel j would be the value aj, okay? So if I calculate the probability of observing a pixel value a given image aj, which implies some rotation, which is wrong now, okay? But we don't care about that for now. The most likely one will be pixel value aj, because we assume this is the true picture. And then how much does the probability decrease as we go away from this pixel value? Well, that depends on how much noise is there on this picture, because this is an experimental picture. It has a lot of experimental noise on it, which we can assume to be Gaussian. Then we can draw a probability distribution for observing the pixel value xj, okay? And the width of this Gaussian, I'll call sigma, is the standard deviation of how much noise is there in your experimental image, okay? Now, we can do that for one pixel. If we now assume independence between all the pixels in the images, then we can calculate the probability of observing the entire image, giving this reference in its orientation, because we assume they're independent, we can just multiply over all the pixels, okay, and put this probability of x j aj phi, okay? Now, as you will know, I'm going in a more humble position. So a Gaussian function looks like this. So if this is a pixel value aj, so it becomes xj, sorry. There's some constant here which I will ignore, okay? If we do a multiplication over many values j, because all the pixels are independent, then you know that x exponent a times exponent b, this you know from your high school. Okay, so you can rewrite this to something with some different constant, and then there is a summation over pixels j, aj minus xj squared divided by minus 2 sigma squared. Okay, where this multiplication outside has become a summation inside. Okay, now you can recognize that's again the same thing that we had here is now here, okay? There's some additional stuff around it, which is this division by the standard deviation of the noise, and it's being exponentiated. But the underlying similarity measure is actually rather similar. Okay. Now, what you then do in maximum likelihood is that you can let's assume we know all the phi's for now, all the orientations of the penguins. Okay. If you would do, then the probability of observing all the images, if observing one image is independent from observing the other images, you can then multiply again over all these. Okay. Now that becomes a bit nasty to work with, and then we just take a logarithm of that. So, and then we can rewrite this for a summation over all images of a logarithm of the probability of observing x given a phi, and this now has an I. Okay. And what you can now do is optimize this likelihood function with respect to the value of every pixel in the image, okay? And you know you can optimize a function by taking the derivative with respect to that value. So if you do that, this becomes a log of an exp, so that disappears. So this becomes something which is very similar to this, aj minus xj squared divided by minus 2 sigma squared, okay? Now if you take the derivative of this, that will be something like minus 1 over sigma squared times aj minus xj, right? And the squared has gone there with the 2, which disappears. You set that equal to 0, and you solve for a. So then you can see that aj becomes, I lost a sum somewhere. aj becomes sum I xi divided by the sum I of 1, which becomes n, if there's n images, okay? So then, if we knew all these phi's, optimizing the likelihood function is just taking the average of the images, okay? That was a little to the side. If you don't like formula, come back to me now. Okay, if you don't know the phi, if you don't know the rotation of your image, okay, then that goes into the formula here, and you can then actually take, I don't know what what orientation every image is in, but I can calculate the probability that given a certain rotation and the average, what's the probability of observing my image? And then what it boils down to, you can put an integral over phi, have something where you can put priors about phi, and if you then solve this and do something similar what I just did here for the simple case, you will get to an algorithm where the average of the particle is not just a straightforward average of the particles which are aligned, but it will be something like summation over all the particles and then some integral over the probability of having that, and I won't go into detail, divided by phi p phi x. Now what that means is this is a weighted average, okay? This is of the formula some weight I times xi divided by some weight I, okay? So what we're doing now, rather than in the maximum cross-correlation approach, where we decided on which was the best orientation for every particle, and then did the average, and then iterated round, now we're calculating a probability for every one of the orientations, and for every particle, the particle is added to the average as a weighted average according to those probabilities. And to illustrate that, I've put on this picture. So if your penguin is lying sideways, okay, the probability of observing the penguin in this orientation, if this would be your reference, would be very low. That is why it's rather transparent, okay? Only when I start rotating it, the probability gets a bit higher because this looks more like my reference than this, okay? And then only when it's up in the right orientation, this square difference which we had there becomes small, and thus the probability becomes large. So this has a relatively large probability. And then it goes down, perhaps upside down, because it's not that different at very low frequency from upside up, gets some kind of intermediate probability. And the average image for our next iteration, because it's a similarly iterative process, just becomes not just every image goes in one orientation, but every image goes in with all the orientations. And then these are kind of normalized so that every image in total goes in with a total weight of 1. okay? So that's the main difference between these maximum likelihood approaches and the maximum cross-correlation approach. In fancy terms, it's called marginalization, but it boils down to having probability-weighted assignments of your missing parameters, which in this case are the orientations. Something very similar, of course, happens in X-ray crystallography, where you do phasing and you don't know the phase, and you have these Mickey Mouse plots where you kind of calculate figure of merits over phases like probability-weighted averages. Okay, so this we iterate again. Okay, and if you want to think more of it in intuitive terms, then you can think of it, why would this be a good idea? You do not assign discrete orientation if the noise in the data doesn't allow it. So the cross-correlation plot for the penguin that I showed before was not very noisy, because the penguin images I put up were not very noisy. It was just a scribble of me in PowerPoint. Okay? If there is a lot of noise in the image, like we've seen on some of the images before, then the actual cross-correlation plot for all the orientations can become extremely noisy, okay? And it could be that this is the true orientation of that image, but just because there's so much noise, this happens to be a slightly higher cross-correlation value. And if you then do maximum cross-correlation, what will happen? You'll just assign a wrong angle, okay? Hopefully it will get better as your reference gets better and you might get away with it, perhaps not. What maximum likelihood does different, it puts this value of cross-correlation or squared difference into this exponentiation, and it will calculate a probability, which we could, to some extent, just replace this here. Okay. Now, if there's so much noise in the data, you can't distinguish whether it's this view or this view, then they just go in with rather similar probabilities. So you kind of postpone taking that decision until you hope at some point it will be easier to make. Okay, that's a bit of an intuitive explanation to it, but that works actually better in terms of convergence behavior. Okay, so does that then mean that these two methods are very, very different, or are they at war with each other? No, because as you've seen, the square difference term goes into both of them. Okay, there's the exponentiation of the square difference term divided by 2 sigma squared minus. Okay, that means that if sigma squared becomes 0, the two techniques actually become exactly the same. So if you have data without any noise in it, then it doesn't matter whether you do maximum likelihood optimization or maximum cross-correlation optimization. So that's where I always say, if your data doesn't have any noise, you should use a maximum cross-correlation program. Okay. If you want to read more about maximum likelihood theory, we wrote a review which is in Methods in Enzymology. Okay, now let's go to two-dimensional classification, because our system until now has been very, very limited. Okay, just one reference that we're aligning, just one image of a penguin. Okay, now in reality we have three-dimensional objects that fall into many different orientations and could be in different conformations. So if we think of the data in terms of different 2D images, there are many different views and different classes as well, and all of those would need to be separated in something called 2D classification. Okay, now the way it works, you just extend what I've told you before. And now, rather than having only the missing data, these rotations, we add another type of missing data, which is a class assignment. Okay? We're going to take 2 initial references, and they're a bit different, and I'll come back in a moment how they're different. Okay? And for all our experimental images, we're going to compare every very noisy experimental images in all rotations and translations with each of these different 2 different classes, okay? So not only are we going to calculate probability for every orientation, but it's every orientation for every class, okay? So we're just expanding our array of missing variables. And if we do that, we again take our new averages as probability-weighted assignment over all these different rotations and the 2 class assignment, okay? So now it can be that one particle, this particle, could be, because these are very similar, it could be that 55% of the weight goes into all these orientations, and the other 45% of the weights go into these orientations, okay? So that just means there's so much noise, I don't really know yet whether it's class 1 or 2. It's slightly more likely to be class 1, so I will assign that 55% of all the probabilities, but it's not I'm not sure yet. So that's where a cross-correlation coefficient approach would just say, oh, it is class 1, and I'll just go on iterating. But here we're slightly more conservative, if we like. Okay? And this, again, we can just iterate. Okay? Now, what we then saw what happens, for example, this is for a real data set. This was on large T antigen cryo-EM projections. There's, of course, a problem here. What do you use as the initial 2 references in the previous example, or here I chose 5, okay? Now, it turns out that these kind of optimization approaches have a wide enough radius of convergence, if you like. You can just start from your entire set of particles. I think these were something like 7,000 cryo-EM images, and you can randomly divide them in 5 subsets, and without any alignment whatsoever, you can just average those 5 subsets. And because these particles are actually a bit elongated, they're decamers, but if you don't align them, then you'll get something like is shown here, which is more like a circular-like feature. Okay? Now, there is no biological information whatsoever apart from the radial distribution of density in this particle in these initial references, and the differences between them are just based on the random subsets. Okay, so there's no real differences between them. It's just different random instances. Okay. Now, if you take all your particles and start aligning it against these 5 references at the same time, so calculating these probabilities for every orientation that it belongs to reference 1 and 2 and 3 and 4 and 5, and you iterate this through, then you can see you can get to, it converges to something where you can start making sense of the data. And this was a relatively bent form of the particle, and you could see some little piece of DNA sticking out. This was a straight one, etc. Perhaps these were hexamers rather than dodecamers. So the good thing about 2-dimensional classification is, without you providing anything else than the number 5, which was the number of references you're going to use, you don't put anything in. You put your data in, you put 5 in, and then you just let this algorithm converge. Okay? And that's nice because it then becomes very objective. Apart from the number 5, nothing of your expertise or bias goes into the procedure. And these kind of methods, a bit modified variants that I will speak to about in a minute, are extremely powerful to clean your data and assess how good it is. Okay, let's move into 3 dimensions now. Okay, so I'm putting back up the Fourier duck from Tony's talk. So remember that the 3D transform, the projections of a 3D object were central slices through the 3D transform. Okay? Now, in 3D, we can do something similar as we've now done in 2D. We have some initial model, and here the situation will be slightly more complicated. I will come back to that in a few minutes. But in the computer, we can make projections either by taking these central slices out of the transform or by doing the real space line integrals. And we can just make computer-generated projections of this model in all the directions. And then we compare with experimental projections, which are very noisy, that's not shown here, and see we can calculate similar probabilities as there, or cross-correlation coefficients. Again, we have the choice. For example, if we do cross-correlation coefficient, and we see that this view fits best with that projection, then we assign it there. Okay? And we can do that for a whole bunch of experimental images. And then at the end of what would be one iteration, we then have orientation for ED particles, and then, for example, using the fact that they're the Fourier slice theorem, we can put those slices back in the right orientations in the 3D transform and do an inverse transform to get back to something which is now better. It's a better representation of what's really going on in our data than this initial crude model, which was just an orange puppet. Now we have something which is actually not perfect yet, because the same happens as with the bad initial penguin image, because our reference wasn't perfect, our angles aren't perfect, and therefore our reconstruction isn't perfect. But again, it's better hopefully than that we had, and we can keep iterating until the angles converge to some point where hopefully we have a correct 3-dimensional reconstruction of our 2-dimensional images. Okay? And here, again, the parallel with maximum likelihood is very similar. Rather than assigning one direction to every particle, you now take every particle. This would be the most likely direction, so that goes in with the highest weight. But perhaps it's not so easy to see whether this is from the left or from the right. So this one also goes in with some non-zero probability. Okay, all of them go in with non-zero probability, but some of them will go very close to zero. Okay. And again, do not make hard decisions if the noise impedes this, is an intuitive way of understanding this. Okay? Now what is important, very important to realize, that any of these procedures in 2D or in 3D are all local optimizers. Okay? They will start, if there's some very complicated energy landscape, because there's all these parameters that we need to optimize, then it will just jump into the nearest local minimum. Okay? That's not something only maximum likelihood refinement. Most approaches in the field are based on local optimizers and will suffer from the same. But that's important. One consequence of this is that if we now start from just random orientations, like a three-dimensional version of these circular shapes that I showed for the large T antigen, okay, we could assign random angles to every particle, do some reconstruction, have a spherical thing, then sometimes that works if you start refining that, and sometimes it doesn't, okay? So very often, actually most of the times, we prefer to start from some initial model that makes sense, okay? And Paula on Friday, of course, discussed several of those methods on how to generate such an initial model, okay? And that is, the fact that we need it is because, unlike the 2D case, we can't really start from random angles very often, okay? It also means, because it's a local minimum, if this initial model is very, very bad, so it's very far away from the global minimum, then you'll get stuck with it, okay? So just think bad model in, bad model out, okay? And that's called model bias, okay? And Paula discussed common lines methods on Friday. I think those in particular are notoriously difficult to escape from, because the projections of those models, because they're made from common lines, are actually very nice, but the way they are combined together is a horrible local minimum, okay? Now, if you introduce some form of stochasticity, okay, some random perturbation of the optimization process, think of this as a little ball not just rolling down, but you give it you make it a little rubber ball that goes bouncing about, okay, and you can control how much it bounces, then from a local optimizer, you can, in theory, get a global optimizer, or you get an algorithm that in theory could reach the global minimum, okay? And of course, in X-ray crystallography, simulated annealing-like approaches for refining your model are equivalent to this, okay? So they can potentially reach the global minimum. So if you start from random starts, random angles or blobs, or people have just used from Gaussian distributions of noisy density, if you put in some stochasticity in the refinement, you might get to the correct answer, okay? And that's why programs like the simple algorithm from Hans Almlund and also Monte Carlo-like approaches in EMAN2 by Steve Lutke are gaining in popularity. They introduce some form of stochasticity to get away from local minima, so that you can just put in your data, start from some random blob, and get your final model out. Okay? Now, the bad thing is potentially, okay? You're not sure that's going to happen. If it doesn't happen, and you're only at 15, 20 angstroms, it might be quite difficult to find out that it didn't happen. If you get to 3 angstroms, then you'll see all kind of side chains and so on. You know you're correct. So especially for lower resolution maps, you have to be very, very careful here. And I think Richard, in his talk on validation, will go into some more details. Okay. Now, of course, these are then 3-dimensional machines in different orientations. So what we just did to the 2-dimensional classification, we can now just draw on to 3-dimensional classification. So rather than well, let's first, these are experimental images of of a certain molecule, and this is in complex with a cofactor, okay? And what you would really want to do is separate 2D projection images of these out so that you have all the complexed ones and all the uncomplexed ones in two separate reconstructions and do a reconstruction of both of them, okay? So the way that works is very similar to what we do with the 2D approach, where we now, rather than one three-dimensional reference, we now have two three-dimensional references. And again, if we do this maximum likelihood way, then every particle could contribute to both of them and in all possible orientations with a given probability. We just start with some, you could start with some initial model. For example, if you would know that this complex has something in its hand or not, okay, then you could come up with an initial model like this and an initial model like this to kickstart the process and refine this all the way through, okay? Now, and then hopefully you will end up with a reconstruction of the uncomplex and the complex objects, okay? And I said, again, maximum likelihood, then every particle gets spread out over all the orientations, but also over all the references, in this case, both references, okay? Now, if you know that it has something in its hand, if the complex forms it something in its hand, already knowing it has a hand without a priori is difficult, and that was Paula's methods for initial models, okay? But if there's structural heterogeneity, actually knowing what kind of heterogeneity is there is very, very difficult, okay? If you have a very well-studied system with known structural states, for example, a ribosome, that would be perhaps relatively easy. If you have anything that's not a ribosome, probably it's hard to know what kind of structural variability there is. So if you'd have to come up with some informed n number of different references that would describe such a heterogeneity, that might be difficult to come up with, and more importantly, it would also be very dangerous because of this model bias, because you might actually bias your entire classification on something which you think is true, but isn't. So it turned out that these maximum likelihood classification algorithms are a good solution for that. And as an example, I'll show you here a 70S ribosome where Joachim Frank did a reconstruction to about 10 angstroms, and they saw fragmented density for elongation factor G. What you can now do with the 3D maximum likelihood is you filter this to 80 angstrom low pass, and this we like to do. We like to low pass filter our initial models to still have enough so that we can start our iterative process to get ever better maps. But whatever is somehow wrong in this model is removed from it so that bias towards it doesn't play a role. Okay? And then again, just like in 2D, we took 5 different random subsets for large D antigen. We can do the same here. We do 4 random subsets of our particles, and you can do one iteration of this matching of projections of this model with each of the random subsets. And then you get 4 randomly different 3-dimensional maps of a ribosome. They're slightly better because they've been aligned with respect to this initial model for one cycle, okay? The difference between them are only based on random instances, so they don't mean anything biologically yet. But again, we can do the same trick. We can now refine all the entire data set of particles, so join all 4 random subsets together and do this iterative refinement. And then we found we could actually separate with and without EFG, and then the state without EFG had 3 tRNAs and this one had 1, okay? So that's good, because this we call unsupervised classification as opposed to supervised classification. In supervised, you tell it has something in its hand. In unsupervised, you don't tell anything else than the number of different structures you want to refine. In this case, I told it to refine 4, but actually 3 of them are very similar, and these we just interpreted as the same structural class, and we joined all those particles together. Okay? Good. Now, the last part, let's move into Fourier space again. Okay? Until now, I've only spoken about pixel values in the images. Okay? Now, in lecture 2, we've seen that the Fourier space formulation is much more convenient for a number of reasons, taking projections, slices, etc., but also the effects of CTF, which were a convolution operation in real space, which is very difficult, become just a multiplication in Fourier space, which is much easier. Okay? So keep this in mind. What we're going to do, we're going to change our real space model, where an experimental image was a convolution of a projection of a 3D map with noise, to Fourier space, where now we have again, this is now taking a slice out of a 3D transform, and this becomes a multiplication, okay? Now these multiplications are much easier to deal with in the computer than these convolutions, okay? And the type of noise we're going to add on this is now different, because what we can do, whereas here we had one pixel value for a reference image and a Fourier and a experimental image, okay? Now we're going to take the two-dimensional Fourier transform of a projection of our three-dimensional penguin and compare it to the two-dimensional Fourier transform of our experimental image, okay? And those are complex numbers which I haven't really gone into detail, but you can plot them in the 2D plane. Then this is your Fourier component for the experimental image. Then this is the value of the Fourier component in the experimental image multiplied by the CTF of this image, okay? And then we can, now the neat thing of Fourier space is, because we know, and this we saw in several of the lectures before, is that the signal to noise ratio in your images decreases as a function of the spatial frequencies. So as the images contain finer detail, they become noisier, and the low frequency information is still relatively low in the amount of noise. What that means is that the width of these Gaussian functions, which in real space we had just this value sigma here, we could do the same thing. We could use one value of the standard deviation of the noise for all the Fourier components. But the nice thing of Fourier space is we can do better, because we know low frequencies are less noisy than high frequencies. We can make a resolution or frequency dependent amount of noise on every Fourier component, okay? I will skip quickly over the formula, but this now describes noise which is not independent in the real space. It's actually colored noise. Okay, and these are some spectra, because as we were optimizing these functions these log likelihood functions for A, we can also optimize them for sigma. We just take derivatives with sigma and solve them for it, and then we can actually estimate from the data themselves how much noise is present at every frequency in the Fourier domain. Okay, good. Now that brings me to the last part of the problem, which was ill postproblems. Okay. Now the good thing about all these maximum likelihood estimators, under some conditions you could say they're the best one can do, and one of those conditions is in the limit of infinitely large data sets. Okay. Now that's never true. Even if you do automated data collection on the cryos for 2 weeks in a row, that's still not true, and that kind of hurt. Okay. Now the bad news about ill postproblems is that the experimental data on itself might not be enough to determine a unique solution to the problem, okay? There is somehow so much noise in my images that I can't really be, I don't have enough information to get the true underlying signal out of there, okay? Now, or in other words, there are many noisy kind of averages or reconstructions that describe the data equally well, and then how do I know which one is the true one? Okay, and that then involves danger of incorrect interpretation. And there's some good news as well, because you can solve many of these ill-posed problems which don't have a unique solution by adding in additional information. So prior information that I have about my structure can help to distinguish between all the noisy reconstructions that could be possible based on my data, which is the most likely one. Okay, that's called regularization, in other terms. And conventional approaches to it have been Wiener filtering, which we'll come back in a moment, but most of all low-pass filtering of maps. Okay, so what people would do, they would have some initial three-dimensional model, they have all their images, they do this projection matching I just described, they do a reconstruction, and because of the noisy character of these images, this reconstruction becomes very noisy. If you would just go back straight in here, as I mentioned before, then the amount of noise in this reconstruction would go up and up and up, and that's because of this model bias effect, that something bad going in, something bad comes out. You might actually get ever more and more noise if you do this. So people realized this very early on in the field and started doing all kind of low-pass filtering, as we saw in lecture 2, that reduces these high-frequency noise components before they actually go into the next iteration. Okay? That was all good and it works very well, but the problem is there were many, many different ways and different implementations, and they all had their own kind of ad hoc parameters which you would need to tune carefully. If you're greedy and you don't filter much because you really like to see those high frequency components, then this noise might creep up and up and up. And Richard will describe that in more detail in his lecture as well. Okay, that's called over-refinement or overfitting. Okay, now you can do regularization also in a statistical manner, and that's where Bayes' theorem comes in, because you can postulate a posterior where you actually have the likelihood function that we had before, and we multiply it by some kind of a prior. And the prior means what's the probability of getting a certain model. So I don't know anything about, if I have my data and I want to reconstruct the model, what do I know about models, about reconstructions of EM density for proteins? What do I know about them that could be useful as prior information? Okay, so that's the important question. And this we've done, sorry. The thing that we came up with is that in Fourier space, again, you can assume that the signal actually has a limited power, okay? And a limited power in Fourier space means it's actually smooth in real space. So in one point in real space, if you move a bit to the left, right, up or down, then the changes in density will be relatively small compared to the density values, okay? And you can express that in mathematical terms, which we don't have time to go into detail to, okay? But you can now do similar things as we've done here, just setting derivatives to a target function to 0 and solve it. It becomes a bit more complicated. But what you get is an algorithm where you can calculate values for your new map from the images, okay? And every image is multiplied by the CTF, and then its probability weighted average over all the rotations and classes, if there are as well, are all added together, and they're divided by something which has the square of the CTF, okay? And then there is an additive term. And for those of you who are used to looking at these kind of formulas, you'll recognize that this is actually a Wiener filter-like approach, okay? Now what this will do is, it's two important things. It will correct for the CTF, so all these modulations where the things went through 0. If a CTF goes through 0, well, at that point you multiply by 0, and that particle just doesn't add anything into your reconstruction. If your CTF is 1, because that's where your CTF for a given particle is optimal, then actually that particle goes into with a weight of 1. So you can see how this taking images at different d foci and having the 0 passings at different places gets corrected for in a formulation like this. Also, because of this prior that we had, that we said that the power has to be limited, we have some additive term here, and what that does, I won't go into detail again, but it will actually low-pass filter your map. And it will do so based on two estimates it makes. So by taking derivatives towards sigma, which was the standard deviation in the noise of your images as a function of spatial frequency, it will calculate these resolution-dependent power spectra of the noise from the data themselves, compare them with the power spectrum of the signal that you're actually reconstructing, and combining all that into something that not only corrects for CTF, but also low-pass filters your images in an optimal manner. Okay? So this does, without you having to tweak any parameters, because it's learning the noise and signal spectra from the data themselves, it does some form of this low-pass filter that you previously had to tune yourself. Okay? What you then get out are images that are CTF corrected, and I just wanted to show you because many people have looked at 2D class averages like this. This is a 2D class average of beta gal calculated in RELION while switching CTF correction off. Okay? And you can see it is a gray image with a black halo around it and then some white density inside. If you do full CTF correction, then you get an estimate of the true Coulomb potential in or the projected Coulomb potential in your images, and that's actually white on a black background. Okay, and we've seen something very similar earlier on in lecture 2, where we had the CTF of max, and if you don't correct for CTF, then you have all these. Then it's gray with all these black halos around it. Okay, now that brings me to an end. So let's recapitulate. I think image refinement in 3D electron microscopy is good to understand it as an inverse, incomplete, and ill-posed problem. Because it's inverse, we need these iterations to solve it. It's incomplete, we need this marginalization, which I hope you now know means this. It results in this probability-weighted assignments of orientations and classes. And because of the ill-posed nature of the problem, we need this regularization, which rather than doing all kind of ad hoc approaches of filtering and so on, we can actually learn by optimizing this regularized likelihood function. So this does all three things in a single function. So rather than having a box of different programs doing each step, there is just one function to be optimized in one program. As I've shown you, you can do that to calculate 2D classes, but also 3D classes or 3D refinement. 3D refinement in this context is nothing more than a 3D classification with a single class, although, as Richard will point out, there's something to prevent this overfining and overfitting, which is a detail in this respect to that, okay? So because it learns all these parameters, the spectra of the noise and the signal from the data, there's very few ad hoc parameters to tune by you, and that's why it really isn't that difficult anymore to learn image processing for cryo-EM. So I think the most difficult part to learn is make your samples and do the imaging. Once you get here, things have been more difficult in the past, let's say it that way. Okay, so let me just put this slide up by Tony about the recently solved near atomic resolution maps. All three of them were calculated by a RELION program that uses this regularized likelihood approach that I've just mentioned. Okay, and because this lecture doesn't tell you at all how to actually do that, okay, and it's not part of this course, which is theoretical, I thought I'd draw your attention to this tutorial, which I'll give for in a CCP-EM workshop, which will be in October at Harwell, and possibly I'll also do a local copy here, so that we don't all have to go to Harwell. Okay. Just one last slide with some practical tips if you start doing this. We always perform two-dimensional classification before we go into 3D reconstruction because it's a very powerful means of cleaning your data set. Bad classes usually have particles that should not be in your 3D reconstruction. Throw them out. The quality of 2D classes often gives a very good measure of how good your final 3D reconstruction will be. If your 2D classes only look very blobby and everything, you can't see any details, don't expect your 3D reconstruction to contain any details, okay? And the things you have to play with is then the number of classes, where for cryo-EM, I like you to have at least 100 or 200 particles per class, whereas in negative stain, you can go to much fewer, okay? Then because many of our proteins are these machines which use conformational changes, many of them are complexes which might fall apart. We always check for 3D heterogeneity by doing these 3D multi-reference refinements. Again, the number of classes is the main parameter you have to play with. And just finally, that some people are very keen on letting EPU run for 2 weeks and get 2 or 3 million particle images, okay? Now, we actually prefer smaller data sets which are of better quality, and it becomes computationally much cheaper to do this, okay? All these regularized likelihood optimizations aren't computationally cheap, so if you have to pipe through 3 million particles, that will take a while. And not only that, if your data set is high quality, so if it's clean, just a few particles, but all of them count and are good, then the reconstructions you get out are typically better. And because it becomes very computationally expensive to process 3 million, what often happens if you have 3 million, people just don't clean it that well, and then the reconstruction somehow gets more fuzzy. Okay, that was it, and thank you for your attention. If there's any burning questions, I can take them, or otherwise we go for coffee.
So I'm going to ask about this number of classes, the 5 in the 2D case and 4 in the 3D for the right.
Yes.
I think. So from what you're saying at the end, it looks as if you decide the number of classes by the number of particles you've got. Or what happens in your case? The ribosome, for example, you took 4 classes and it didn't matter that 3 of them were the same. But
Right.
what happens if you take too few? Is it immediately obvious from the quality of the images that you get that you're not allowing for some variation?
Yeah, if you take too few and you're still averaging over distinct conformations, if you look at the density, you can probably see it's fuzzy or... so usually there's indications you're not there yet, but to some extent the density is always fuzzy because it's always some compromise, right? So it's really something, that's why there was the word play on the other one. Playing is, we do play with this a bit and we use different numbers and see what comes out. So too many classes, in 2D, if you use too many of them will go to 0 actually because of how the optimization works. In 3D that doesn't happen that much. Typically it's not a good sign if you use a number of 3 classes or 4 classes or 5 classes and the data just always goes into classes that are of equal size. That typically is a bit suspicious. That usually means something is not being done well yet, okay? If you use way too many, if you use 15 classes, then computationally it becomes very, very difficult, especially 3D takes then a lot of memory. I think the highest number we've done, Rebecca, you use 10, right? 10 3D classes for her ribosome structure. I think that's about what you should use.
Scale linearly with the number of classes? Or?
The memory usage does, and the CPU as well, yes.
Just following up on that, could you rewrite the maximum likelihood function to have a dimensional number of classes so that you didn't have to put anything in there?
I don't know how to. So this problem in cluster analysis or just pattern recognition is it's a well-known problem, and people have done neural networks that grow, and usually it leads to algorithms which are even much more computationally intense, and the advantages of that are typically not that big. But yeah, so perhaps.
I was wondering, instead of relying on looking at your images to come out and saying it's blurry here or something like that, do you get a sort of a local variance for how well the different images
Yes.
are matching to that you could see there's a high local variance here and maybe we need something that's here some of the time and not
Yes. Perhaps that's something to include for Richard as well. We can calculate 3D variance map by bootstrapping. Powell Panzak wrote a nice program for that. So you do reconstructions from random subset with repetition from the data and then calculate variance between those, and you can see whether there's any unresolved hotspots, okay? Or often what we now use is, which will be also in Richard's talk, is local resolution maps. So if your structure is homogeneous, and then what should happen is that the resolution variation throughout the 3D map should be very small. So all parts would be more or less equally detailed. Okay, that's a more numerical way of saying that one part looks fuzzy or not, right? So you can look at local resolution map and 3D variance map to kind of help you in that assessment, yes. Once your eye is a bit used to it, you can just see it. I mean, it's just blurring of density, but yeah, there's numerical ways. Minded?
So if I understand correctly, by averaging, you sort of assume that the noise is random and therefore it will go to 0. But is the noise really random? Because you have carbon on there, you use carbon, so it contributes a signal that you're not getting rid of.
Well, there is carbon, but the carbon is different for every particle. So that the carbon is never aligned, if you like.
But it's
So
never 0.
no, it's not. The noise is not 0, but it is random. We can discuss whether it's Gaussian or not, but yeah, it is random. The instances of carbon are different for every particle.
Right. But on average, they're not 0, so you don't get rid of
They're not 0.
signal. So how doesn't that end up in your reconstruction?
If you average over many instances of numbers that are different but not 0, then it will disappear from the average. It will become a constant. Okay? If there are no more questions, see you all tomorrow.